Now, Chapter 18 is not on this exam, but it does provide a formula that if I have a normal random variable z, I can calculate the expected value of e to the sigma z. It comes from the moment generating function formula, the moment generating function formula of the normal. Namely, the expected value of e to the sigma z is equal to this expression. The reason that's important is if we go back to the formula we had for x, we can take an expected value of x of t, because the only thing that's random is the z term. And that's what that moment generating function formula allows us to do, that the expected value of x at time t is the initial value. This, of course, this exponential is just a constant, so it factors out, and then we use that result for the z term. And notice that geometric Brownian motion, the alpha, which is always referred to as the instantaneous return, continuous return, notice that this is consistent with this derivation, namely that the expected value of e to the xt does not have that half sigma squared adjustment in it. The expected value of x of t is x0 times e to the alpha t. So, and you might be a little bit confused, but there's a difference between the in the model of this type, the expected return is equal to alpha minus a half sigma squared t. That's the expected return. But when we do this calculation, the expected value of x, that's not equal to x0 times e to the expected return. That's the point. The expected return over the period is smaller than alpha, and it reflects the variability of the returns. This formula says that the expected value of x is equal to gives you a return of alpha that's bigger. So you can think of alpha as being like the arithmetic return over the period. And you can think of alpha minus a half sigma squared as being like the compounded effect of geometric return. So that the expected return over the period is reduced by variability, but the expected value of x does not reflect that variability. In an earlier module, we talked a little bit about the relative importance of the drift and the volatility term, or the drift and the noise term. It's very common to call the dz term the noise term because it produces the variability, and sometimes Brownian motion is referred to as white noise, a perfectly random sequence. Well, over short periods of time, I mentioned before that the noise term, the volatility term, dominates. And that's because if we look at the ratio of, in the numerator, the standard deviation divided by the drift, our intuition is always that square root of h is smaller than h. And that's because in general when we're taking square roots, we think of the square root of 9 as 3, the square root of 25 as 5, and so forth. But if you graph the square root function, what you realize is the square root of a number is only smaller than that number when the number is bigger than 1. And here we're dealing with h values that are smaller than 1, in particular converging to 0. And for those values, the square root is significantly bigger. It's an order of magnitude bigger than h. And so you can see why, if I take the ratio of the standard deviation term to the drift term, I get an expression which blows up. namely that the standard deviation becomes infinitely more influential on the drift, on the movements of a stochastic process than does the drift as h gets smaller and smaller. When h is big, it looks like the drift is dominating. But as h gets smaller, this ratio going to infinity tells you that the effect of the standard deviation term will grow to be infinitely more influential on how the process behaves than will the drift term. And we can see a numerical example of that in this table. It's just a simple numerical example of what that formula tells you. And you can see that, you know, if you're looking at periods of a year or greater, the ratio is smaller. But for periods less than a year, h less than 1, because we're measuring time in years, we see that the ratio of the volatility to the drift term gets increasingly big. In fact, by the time we get to a minute, what we're basically saying is if we're modeling time in minutes, that over any 1 minute period, the effect of the volatility term will be 700 times greater than the effect of the drift term. And as we make time smaller and smaller, this factor grows without bounds.